Welcome everyone, and thanks for joining this presentation on LLHD. My name is Fabian, and I'm a PhD student at the Integrated Systems Lab of ETH Zurich. Me and my co-authors Andreas Kurt, Tobias Grosser, and Luca Benini have developed a multi-level intermediate representation for hardware description languages. The workflow we use today to design digital circuits, including CPUs and GPUs, has a severe redundancy problem. The sheer complexity of modern chips, where we need to place billions of transistors and iteration is extremely expensive, has given rise to a very deep design toolchain, much more so than in software development. Along their way to becoming silicon, digital designs pass simulators, synthesizers, logical equivalence checkers, formal verifiers, and many other tools. Hardware description languages are used as the input to these tools, with System Verilog and VHDL being widely used in industry. Both languages have grown organically over time and are very hard to implement, with standards spanning over 1,000 pages. Each tool vendor has their own proprietary implementation of the complex language frontend. The standards can be very subtle, and it has proven extremely difficult for the tools to implement them consistently. As a consequence, designers resort to a safe subset of each language known to produce identical results across tools, which precludes the practical use of many distinguishing language features. Innovation on the language front is severely hampered as well, since novel languages need to funnel through one of the existing HDLs. We observe that the hardware engineering and compiler design communities have evolved in isolation, even though many optimizations and methodological improvements readily apply to both worlds. This is to hardware engineering's severe disadvantage, as we see ample opportunities for the communities to connect, exchange, and benefit from each other, which is why we propose LLHD. LLHD is an IR for chip design. It allows us to develop a single frontend for HDLs, which we call Moore. Moore is to LLHD what Clang is to LLVM. We develop it alongside LLHD in an effort to get System Verilog and VHDL right once and lower them into a language that is much more amenable to further use in various tools. New languages can now target LLHD directly, which offers a significantly lower semantic surface area than HDLs. As part of LLHD, we propose a lowering of the behavioral semantics in a System Verilog and VHDL to an unambiguous structural representation that is much easier for tools to ingest. Simulation is now already possible on the IR level via open source simulators developed as part of LLHD. All of this allows vendor tools to ingest a simple IR and produce the same IR again. In a sense, the various tools become yet another transformation pass in the IR pipeline. A hardware IR must cope with the intricacies of digital circuits, which differ substantially from software. For one, digital hardware is inherently time-sensitive, due to the time it takes for signals to propagate through gates and the presence of clocks. More so, chips are inherently concurrent, as the logic gates and subcircuits sit next to each other on the manufactured silicon. And finally, the sheer size of modern chips with billions of transistors require heavy replication and hierarchical design to enable us to place circuits of this complexity. LLHD was heavily inspired by LLVM. It uses SSA form, has basic blocks and fine nodes, a similar naming scheme, and a similar type system. Besides the usual set of instructions, LLHD provides hardware-specific instructions though. For example, the wait instruction suspends execution and resumes at a later point in time. This is similar to how async await or yield works. The ability to suspend and resume is essential to behaviorally model concurrent control flow. Another example is the drive instruction, which schedules a signal to change at a later time. This models the timing effect of digital gates, but also allows for behavioral modeling of registers. Finally, inst allows processes and entities to be instantiated. LLHD draws from the abstractions established in modern HDLs over the past decade and distills them into fundamental orthogonal concepts, which take the place of functions in LLVM. Entities build hierarchy by instantiating other processes or entities, which then operate concurrently. Additionally, they can contain pure data flow instructions, providing a structural circuit description. Processes are Turing-complete subprograms that behaviorally describe how a circuit state and output reacts to a change in its input, which is common abstraction in HDLs. Finally, functions facilitate code reuse and recursion. They do not have a direct hardware equivalent and cannot suspend execution. LLHD is separated into 3 levels to cater to the different parts of the chip design flow. Behavioral LLHD aims at capturing circuit descriptions in higher-level HDLs as easily as possible. It allows for simulation constructs and test benches to be fully represented. This includes assertions, file I/O, or formal verification information as intrinsics. Structural LLHD limits the description to a subset that describes the input-to-output relations of a design. This makes it easy for synthesizers and other tools to ingest, since no more control flow is present. Netlist LLHD further limits the entity bodies to contain only signals and instances. This captures the hierarchy of a design, but all semantics have been removed. Synthesizers commonly produce this level of abstraction. This structure allows LLHD to clearly capture a full design for verification, the parts relevant for synthesis, as well as the netlist that results from synthesis. As part of this, we propose a lowering from behavioral to structural LLHD that uniformly maps the behavioral semantics of an HDL to a structural representation. Let us briefly discuss how we can map existing hardware description languages to LLHD. Throughout the industry, a large part of RTL and verification code is written in System Verilog and VHDL. The hardware world is very slow and conservative, due to a design flow that is geared towards reducing the number of design iterations as far as possible and adopting a first-time right mantra. So whatever we do, System Verilog and VHDL legacy code must be part of the story to have any chance of adoption. Let us consider a simple accumulator circuit that adds numbers as a running example. Our design is split into the RTL code shown at the top and the verification code at the bottom, which is a common industry practice. Let us start with the RTL code. Processes such as always-FF and always-comb in System Verilog map directly to an LLHD process, with a list of ports implied by which variables the process reads and writes in the System Verilog code. The always-FF process describes a flip-flop. The passage condition, indicating clocking behavior, is translated into a wait instruction, alongside logic and branches to detect the rising clock edge. Assignments directly translate to drive instructions. The always-come process describes a combinational circuit. The body of the process is translated directly to LLHD, and the behavior of reacting to changing inputs is translated to a wait statement at the end of the process. Finally, the accumulator module itself instantiates the two processes alongside additional signal wiring. Verification code is the more involved part. Since these pieces of HTL code do not need to be synthesized into hardware, they require less strict adherence to design and coding guidelines and can essentially contain arbitrary code. Starting simple, functions in System Verilog translate directly to functions in LLHD. Verification constructs, such as assertions or file I/O, is mapped to LLHD intrinsics, similar to LLVM. Initial processes, which are a particular System Verilog construct used mainly in verification, map to processes in LLHD. The initial behavior is achieved by halting the process once control flow reaches the end of the process body after the first run. Wait statements in System Verilog translate directly to wait instructions in LLHD, even when buried in loops, and function calls map to corresponding call instructions. Finally, the test bench module itself simply instantiates the accumulator and the initial process. The emitted code when translating from HDLs is very high level and generally behavioral in nature. While this is convenient for a language frontend, it is rather unwieldy for synthesizers and other tools further down the pipeline, which benefit from a more structural description with explicit registers and lack of control flow. LLHD implements the lowering from the behavioral to the structural level as a chain of transformation passes, similar to LLVM. The general objective of this lowering is to replace branches with branch-free code. In the first step, we apply basic transformations such as constant folding, dead code elimination, common sub-expression elimination, and instruction simplification. These are equivalent to their LLVM counterparts and try to reduce the complexity of instructions. In the second step, we apply early code motion, which is a first hardware-specific transformation. Its goal is to move arithmetic out of basic blocks to facilitate later control flow passes. This is similar to loop-invariant code motion in LLVM, but operates in an eager fashion. If we look at our accumulator again and apply these basic passes, we can see that the highlighted instructions are moved upwards in the control flow graph. We take special care not to move probes across wait instructions, which would alter the semantics of the circuit. Temporal code motion is a novel pass that tries to move drives out of basic blocks. While doing so, the condition under which the control flow would reach the original drive is annotated as a separate condition on the instruction. This allows us to make drives control flow independent. Doing this requires a few tricks. For one, the capability of wait instructions to suspend execution separates a process into distinct temporal regions. Each region is a set of basic blocks among which time is guaranteed to never advance and signals never change. We can use these temporal regions to reason about the synchronicity of instructions. For example, we move drives into the unique exiting block of their temporal region, which makes the drives always execute at that point in time. In our example, applying temporal code motion moves the drive instructions out of the conditional branches and into the exiting blocks and annotates the appropriate drive condition. In the upper flip-flop process, an auxiliary exiting block is created to ensure all control flow out of the temporal region passes through one point. We now want to replace control flow with data flow, which essentially means replacing branches and fine nodes with multiplexers. This is possible since the previous passes have left basic blocks bare, essentially canonicalizing them into a form where they consist only of fine nodes and branches. Total control flow elimination reduces every temporal region to one basic block. In our example, applying TCFE simplifies the basic blocks in the flip-flop process and replaces the fine node in the combinational process with a corresponding multiplexer. At this point, we can replace trivial processes with entities. Specifically, this applies to processes with a single block and a wait terminator which is sensitive to all input signals of the process. This essentially describes a purely combinational circuit. Process lowering removes the wait instruction at the end of the process and migrates the remaining instructions into an entity with the same signature and name. In our example, applying the transformation to the combinational process strips away the wait and replaces the process with an entity. For the remaining processes, we would like to identify if they describe a sequential circuit such as a flip-flop or a latch. HDLs expect these to be inferred from signals that are only conditionally driven. The exact condition itself translates into a clock, reset, etc. Specifically, this applies to processes with two basic blocks, two temporal regions, and a wait and branch terminator in the respective blocks. This essentially describes a sequential circuit. Desequentialization proceeds by first canonicalizing all drive conditions into their disjunctive normal form. This form makes it particularly easy to identify logic that is rising or falling edge sensitive or level sensitive. We then create a separate entity with the processor's signature, replace all drives with register instructions, and annotate the identified sensitivity. In our example, applying the desequentialization pass will identify the drive condition as a rising edge and replace the drive with a corresponding register instruction in a new entity. This also materializes all data flow dependencies of the drive in the entity. Finally, for the accumulator itself, we can inline the entities and arrive at a crisp structural description of the circuit. These techniques also apply to RTL code, which maps to similar LLHD. As part of this work, we have developed a substantial research prototype of the proposed LLHD IR, the Moore HDL compiler, transformation passes, and simulators. As a first part of our evaluation, we investigate how designs of different scales and complexities fare when directly simulating their corresponding LLHD code. These designs range from simple filters and value converters up to a full 32-bit RISC-V core capable of running at up to a gigahertz. To this end, we have developed LLHD Blaze as a proof-of-concept simulator. While the LLHD framework comes with a reference interpreter, its simulation performance is rather low due to it being geared towards simplicity and completeness. LLHD Blaze maps LLHD code to LLVM IR and then uses LLVM's JIT execution engine alongside a runtime that implements the event queue mechanism underlying LLHD to execute the simulation. With this first prototype, we can already outperform commercial tools by up to 2.4 times. While we are not faster across the board yet, keep in mind that this simulator was written in roughly half a day, without any optimizations beside basic LLVM passes. At the same time, the commercial simulator has been optimized over decades. The message here is clear. Having a clean-cut hardware IR allows for new tools to be written in a very short amount of time, and it allows us to focus exclusively on the task at hand, rather than first diving into the language front-end rabbit hole. LLHD is neither the only nor the first hardware IR out there. For one, all vendor tools have their own proprietary IR, which we do not consider here because they offer very little practical use outside the respective tool. Most existing IRs are built for the far end of the design flow. This includes synthesizers, placers, routers, etc. The vast majority therefore focuses mainly on a structural or netlist description of a circuit which is amenable to synthesis. Only a few have limited support for behavioral and verification constructs, or for valued logic as it is found in System Verilog. None support the 9-valued logic of VHDL though. LLHD, on the other hand, is the only IR that is Turing complete, which allows it to capture arbitrary HDL inputs and constructs. This makes it purpose-built to cater to the entire design flow, with verification and arcane HDL constructs in mind, rather than only a tool-specific language subset. As a final evaluation angle, we also want to shed some light on the in-memory and on-disk footprint of designs, which is an important aspect for any IR. To this end, we compare the size of the system verilog source text, the LLHD human readable assembly text, an estimate of hypothetical bitcode format similar to LLVMs, and the size of the in-memory data structures. As a first observation, note that the LLHD assembly is consistently larger than the system verilog source code. This is due to the semantic gap coming from system verilog, which offers very high-level operations and implicit behavior. Second, we notice that the bitcode format can be very compact despite this big semantic gap. This makes LLHD attractive to transport designs around. And finally, a full 32-bit RISC-V core occupies merely 1 megabyte when loaded into memory. With this, I would like to conclude our talk. Please check out the Docker image which comes as an artifact with this paper. It has all the tools pre-installed to get your hands dirty with LLHD and try your own system verilog code. Visit LLHD.io to try the compiler online in your browser. Repositories and issue trackers are on GitHub. Pull requests, bug reports, feature requests, and discussion is highly appreciated and very welcome. Finally, if you feel adventurous and have a Rust toolchain installed, take a plunge with Moore directly. Thank you very much for joining this talk, and I'm looking forward to your questions.